A flea is going between 2 points which are 100 inches apart by jumping, always in the same direction, either 1 inch or 2 inches at a time. How many different paths can the flea travel by? If you want to give the problem a try, pause the video now and come back when you have a solution. I'll go ahead and reveal the answer now. Let us look at the last jump the flea takes. The last jump can either be from 1 inch or 2 inches away, and these describe different paths of the flea. Thus, let us denote f of n as the number of paths that exist when the endpoint is n inches away from the flea's starting point. But as we just discovered, the flea can take two different paths to get to point n, namely from point n-1 and point n-2. So f of n is just given by the sum of f of n-1 and f of n-2. This is a recursive formula for f of n that can be solved using known methods of solving recurrence relations. In fact, if you know about the Fibonacci sequence, you'll recognize that this recursive formula is precisely the recurrence relation of the numbers in the Fibonacci sequence, where we add the last two values to get the next one. The way to solve these recurrence relations is to use the method of characteristic roots. For any recurrence relation, f of n is equal to alpha 1 times f of n-1 plus alpha 2 times f of n-2. The characteristic polynomial is given by x squared plus alpha 1x plus alpha 2, which gives the characteristic equation x squared minus alpha 1x minus alpha 2x is equal to 0. The point of this characteristic equation is that any root of this expression is a solution to the recurrence relation, meaning that if r1 is a root of the equation x squared minus alpha 1x minus alpha 2 is equal to 0, then we can write f of n is equal to r1 to the n. Now, since the characteristic polynomial is of degree 2, we know that it will have two roots, and in this case they will also be distinct. Then, a further theorem of the theory states that any linear combination of these roots will also be a solution to the recurrence relation. So, if we have roots r1 and r2, we can take any two constants c1 and c2, and we will get that f of n is equal to c1 times r1 plus c2 times r2. To apply this theory to our flea problem, let's first find the roots of our characteristic polynomial. Since our recurrence relation is given by f of n is equal to f of n-1 plus f of n-2, our alpha 1 and alpha 2 are both 1, so the characteristic equation is x squared minus x minus 1 is equal to 0. Using the quadratic formula, we get the two roots 1 plus the square root of 5 over 2 and 1 minus the square root of 5 over 2, which means that the solution to our recurrence relation is of the form f of n is equal to c1 times 1 plus the square root of 5 over 2 to the n plus c2 times 1 minus the square root of 5 over 2 to the n for constants c1 and c2. Let us call our two roots r1 and r2. Our goal now is to find the correct constants c1 and c2 such that we can model the paths of the flea. Using the first two values in the sequence, which are the number of paths the flea can take when the point is 1 inch and 2 inches away, we can set up a system of linear equations and solve for c1 and c2. Solving for the two constants, we get that c1 is 1 plus the square root of 5 over 2 times the square root of 5, and c2 is negative the square root of 5 minus 1 over 2 times the square root of 5. But we can notice that c1 is just r1 divided by the square root of 5, and c2 is just minus r2 divided by the square root of 5. Therefore, the solution to our recurrence relation is given by f of n is equal to 1 over square root of 5 times r1 to the n plus 1 minus r2 to the n plus 1. And plugging in n is equal to 100 gives us the answer. Now, it turns out that plugging in 100 will give us a number with 21 digits, so we can't really write it down, but the answer is about 5.73 times 10 to the 20. We can see that the number of paths the flea can take grows exponentially, which is usually the case with recurrence relations. In any case, I hope you learned a little bit about recurrence relations and enjoyed solving the problem. If you did, please consider subscribing to my channel, and I'll hope to see you again next time.